Hello everybody, welcome to lab number 2, and in this lab we are going to work with the GP6 analog computer. It's going to be pretty interesting. This lab is really simple. All we do in this lab is give the step response, give a step input to the DC motor first, and then we get its step response. From the step response we calculate the gain K and the time constant tau of the motor system, which we use for modeling it as a first order system, and then we try to emulate the same system using a GP6. So I will just go over the basics of this lab. The connections are the same as the previous lab for the motor. You use the tach, the motor and the encoder. You may hook it up, but we don't really use it for this lab. The GP6 connections we will discuss in detail later, but as for now I would like to show you this.
Okay. The lab. I got it.
Okay, so as you see, we just give the motor a step input, and that's given to the analog output block, and from the input we get the response of the motor. So if you look at this plot, what it shows is that after some time, say 1 second, you give it the step, and then you get some response from the motor, and the magnitude, the steady state magnitude of the output divided by your input amplitude is the gain K of the motor, and the time it takes for the output to rise to 62.8% of its steady state value is the time constant. Note that you have to calculate the time constant from the time the step was applied, not from zero, okay? Because you may make mistakes over there. And just to go ahead and explain the GP6 part beforehand, the motor transfer function looks like this. It's K divided by tau s plus 1, where Ws is the output and Vs is the input. If you solve that out and take the inverse Laplace transform and get it back to the time domain, you get this equation, which is nothing but an integral, and there are two terms, one of them is subtracted. Now we are going to implement that using the GP6. Now the GP6 is nothing but a bunch of op-amps, capacitors and resistors hooked up to make different circuits. You can make differentiators, integrators, all kinds of things with that. So here's how it works. This block represents our integrator. Okay, so this is K divided by 100 tau, comes from this term K by tau. The only reason we do a divide by 100 tau because these lines have a gain of 100, and in GP6 the lines with the gain of 100 work the best, so you should use that. That's why we have the divide by 100 tau. So feed that to the integrator. The output of the integrator, as you see from this equation, goes through another gain 1 by 100 tau, because that is the output Wt, okay, and then you feed it back to the integrator itself. And since this is inverted, it takes care of the negative sign in the equation, and then you have a final inverter from which you get the output. Okay, that's simple enough. We will see how to implement this using the GP6, take data from it, and I'll explain more about the connections then. But now my friend Amin will tell you more about taking data for the actual motor and getting its K and tau.
Hello everyone, this is the GP6 analog computer that we need for this lab. First of all, we need to use the motor in order to take the tachometer output to calculate the tau and the DC gain. Let me show you. It's the same thing that we did before with lab number 0 and 1. We just need to take the data from the tachometer. We're going to use the amplitude 1 and 2 volts for this lab, just 2 values.
And you can also actually just do it with 1. Doing it with 2 values is not necessary.
Yeah. Okay, just run the program. It's the same block diagram that we used before. We just need to build again.
So it's all the same code and everything's the same. That's why we are skipping that part.
Yep. And we're ready to run the program. Just we open the scope, same thing. Fix 3, fix 4, and -4. It's good. And we just run the program. You see? We need just 2 values.
So that's the step response you get when you give it a step input, and we will calculate the k and tau from these.
Yeah. Because I have now the data from the code that we explained before in previous lab. We saved the data here. The program that we just need to use is to load the data, the output that we have. We just have to from the tachometer, and we just need to calculate the tau and the DC gain. As my friend Sayo say that for the final tau, we just need to get the from. It's not from 0. It's just from
the time the step starts.
Exactly to the 62.8% of the step input, and the the DC gain is gonna be just the tachometer output divided by the amplitude. So in this case, we just we don't have to divide it by the amplitude, right? Because we're using just one.
Yeah. So you can either write code to do this or do it by hand, whichever way you choose.
So because I have the data, so I just need to run this program. That's it. And the tau, I name it like final tau. It's going to be 0.0250 seconds in this case, and the final k